All right, 1.2. We today are going to be looking at different pieces of graphs and functions and that type of stuff here. So we're going to go ahead and jump right in. Basically, this first thing here is kind of talking about a graph is just a set of ordered pairs, usually in the format of x comma fx or x comma y. Kind of used to see an x comma y back in Algebra 1, but we'll use function notation quite a bit here today. Just remember that y is equal to fx. That's kind of what that's saying right there. And we're going to dive into this example here. We got that function right there that approximates the profit at a toy company, where x is the marketing cost and fx is the profit, or the y is the profit. So both costs and profits are measured in tens of thousands of dollars. And we're going to use the graph to estimate the profit when the costs are about 30,000, and then we can confirm it algebraically if we want as well. So what we're going to go and do here is figure out, okay, what is the profit going to be when it's about 30,000? Now remember, this is in tens of thousands, so we are looking for 3, which is about right there. And that looks like just a hair above, let's see, what is that? 100 times 10,000, that's going to be just a little bit over $1 million. So we can say about $1 million. So, dollars. Okay, and then you can go and verify these here algebraically by going and taking your equation right here and evaluating for, I guess, let's say f of 3. So let's see what's going on here at f of 3. So that's negative 5 times 3. Let me close that there. Negative 5 times 3, we'll square that, and we'll do 50, or plus 50 times 3 like that. 3 squared, that's going to be, what's that going to be, 9. And then 9 times 5 right there, that'd be negative 45. And then 50 times 3 should be 150. So that'll come out to about 105. Now remember, that's in 10,000, so I guess we need to add a couple extra zeros there to that. And then that'll be our answer right there. So we need to add, let's see, 4 zeros, 1, 2, 3, 4. And that is indeed just about $1 million right there. So that's how you can check algebraically right there. You can also do the opposite here. We could start with a profit value right here. So profit of $1.25 million right there. So what I'm going to do here, I believe, let's see, we need to take off 4 zeros, 1, 2, 3, 4. So we need to figure out what's going on at 125 for your f of x value right there. So I'm going to actually plug 125 into the other side. X, and then we can go and solve for that right there. So this would probably require a little bit of factoring. I'm going to add the 5x squared to the other side, and then subtract the 50x, and then plus 125. Set that guy equal to 0. And then we could go ahead and factor out the 5, or divide everything by 5. That would get you x squared, see, minus 10x, and then what's that, plus 25. Then equals 0, and then you can factor. That would be x minus 5, x minus 5 equals 0, and then therefore that means x equals positive 5. You would split your factors up and set them equal to 0, but we don't really need to do that there. So, and let's go verify that here. It looks like over here at 5, you're at that 125 million, so that looks like that works out. So we'll say that is at $50,000, tying it back to the context right there. So that's how you can do some approximation using your graphing, and also just plugging in your values in evaluating. Okay. Now this next part here is going to talk a little bit about domain and range. They'll also talk about x and y intercepts, but I think that comes up here on this next page here. Big takeaways here is kind of a lot of words, but basically an x-intercept occurs where y equals 0. That's kind of the big thing. And a y-intercept occurs when x equals 0. Okay. If you want to do it, with function notation for a y-intercept, remember you're going to plug in 0 for x, so that's f of 0. And then for an x-intercept, you're going to set your fx, or your y piece, equal to 0. That's just kind of the function notation. Anyways, we're going to look here at the graph and then talk about how to do the domain and range. Big thing you want to take away from this paragraph here is you need to just pay attention. Is unless a graph of the function is bounded by a circle or a dot, you can assume that the function extends beyond the edges of the graph. So it's going to keep going past the arrows, and that will affect how we do domain and range. So our domain is the set of x values that are available in this function here. So I usually just draw little arrows here. Domain is basically how far left and how far right a graph goes. Okay, so if we look here at this graph, it keeps going towards down and left forever. That extends off the page. So we're going to say it goes all the way left to negative infinity. And then the farthest right it goes is this x value right here. And there's a closed dot, so I'm going to put a bracket there. That looks like the x value of 3. So we'll put a bracket right there. Okay, your range is the set of all of your y values. Okay, set of all your y values is how high and how low does the graph go. So let's start with the low part. We can see the arrow takes us down forever. So that'd be negative infinity. And some people kind of get confused. They kind of look at this endpoint and say, oh, okay, so it's from negative infinity to, I guess, that y value of 1 to negative 3. But you want to go to the highest y value, which is actually these little vertices right here. And those appear to be happening at the y value of 1 and 2 right there. So we'll say the range is from negative infinity to 2 with a bracket. So be kind of careful there. It's not negative infinity to negative 3, the endpoint. It goes up to these highest points. Okay, and brackets on both of those. Now one other thing we're going to need here on another problem in just a second here is this fact here that x-intercepts have different names. You can do x-intercepts, are also called zeros, and also called roots right there, because I think they changed the vocabulary coming up here in just a second. Alright, these examples here, you're going to use the graph of the function and you're going to approximate it to y-intercept, and then we'll find the y-intercept algebraically, just like we did on the very first problem here. So look in here. It looks like our graph right here, it seems like it's happening, it looks like it's like 0, comma, maybe like 1.5, maybe 1.4, 1.3, something around there. So that's what I think it is. So algebraically, we're going to go and plug in 0 for x. Okay, so let's go ahead and try that. Negative 2, you got 0 cubed, and then plus 4, and then all over 3. Okay, and then once you do that there, 0 cubed is 0, 0 times negative 2 is also 0, so that comes out to 4, and then over 3, which is about 1 point, you could write 1.3 repeating, or you could just write, 4/3, and that would be your y-intercept. I typically make my students write them in order pairs, so I would recommend you do the same right there, 0, 4/3. That's pretty close there. I said 1.4, that's about 1.3 instead there, but repeating there. Okay, this next one here, the y-intercept, looks like it's about right here. That's up 1, 2, 3, 4. That looks like 0, 4. So now we'll verify that algebraically. We'll plug in 0 for x. Now this is an absolute value function, so it might have been a while since you've seen absolute value functions. Absolute value functions, if you have these absolute value bars, that just means if something is negative, you make it into a positive. The formal definition is how far negative 5 is from 0 on a number line. And you would say it's positive 5 units away. In geometry, we emphasize that distance is always positive. So anyways, when you simplify that, you get down to 4, so you can write your y-intercept as 0, 4 right there. So yeah, that's just a quick little thing. Now, as a reminder here, the absolute value of negative 5, of course we just said in this problem is 5, but also the absolute value of positive 5, that's still 5 units away. So just keep that in mind. Basically, absolute value bars changes a negative to a positive, and that's about it. Okay. Next one here, we're going to find our zeros. Okay. Now you got to remember here, zeros are when the fx piece is equal to 0. Okay. Now before we start that, let's see if we can kind of estimate. Notice that the grid here is in 2s. It's got 2, 4, 6, 8, and so on. This first one here kind of looks, or this one over here to the left, I guess, looks like it's at negative 3. So I think that's a pretty solid estimate, and then we can see what the other ones are. This other one kind of looks like, I don't know, if that's 2 and that's 3, kind of looks in between. That kind of looks like a 2.5. So let's see if we can verify that algebraically there. Not really sure why this is here actually, but anyways, find the zeros there. Different graph. So let's go 0 equals 2x squared plus x and then minus 15. Okay. After that, there's 4 ways you can solve a quadratic equation. Most of the times you can do factoring, which is the way I'm going to handle this. You can use the x-intercepts on the graphing calculator. You can use the quadratic formula. That was that big formula, negative b plus minus square root of b squared minus 4ac all over 2a. Or you can do the complete the square method, which some of y'all are a little bit weak on that. So this one is factorable, so that's what I'm going to do here. To factor something when you got a coefficient out in front, you basically multiply these guys here together, 2 and 15, or negative 15, that's negative 30. I'm trying to find some numbers that multiply to negative 30 but then add up to this 1 or this 1x here in the middle. So that would be, let's see, that would be some combination of 6 and 5. It would be negative 5 and positive 6. All right, and there's different ways you can factor, but here's the way I do factoring. Teach my kids, I call this divide and slide. You divide by the 2 out in front. So you find your numbers that multiply to 30, negative 30, and add up to negative 5. And then you take those numbers and you write them. Actually, you know what? I got my signs backwards here. Let me fix that. What was it? Plus 6. My apologies. And then minus 5 right there. And then you reduce the first binomial, x plus 3. And the second binomial doesn't reduce. So you drag this little 2 out here in front, 2x minus 5, and then there you go. That thing is factored right there. If you FOIL that back together, you should get back to 2x squared plus x minus 15. And it takes a lot of the guess and check out of this here, because that's another way you could have factored is just by guessing and checking what numbers multiply to 2 and then negative 15 and all that. So anyways, that's that there. I call it divide and slide. Then after that, zero product property, set these guys here equal to 0. You say x plus 3 must be 0, so x is equal to negative 3. And then you do 2x minus 5 equals 0. And then you add 5 and divide by 2. That's x's 5 halves, or that's also 2.5. And then we can write those as order pairs. Negative 3 comma 0, and then 2.5 comma 0. And there's your zeros. That's about it there for that section. So now we're going to change gears here. We're going to talk about the different types of symmetries of graphs that you can do. So we'll look at graphs here on the next page and determine what type of symmetry, like what line of symmetry they have. So we have certain names for ones that have x-axis, origin, or x-axis, y-axis, and origin types of symmetry. The first 2 types of symmetry, these are reflectional based. I'll just abbreviate them. And then the last one is a rotational based symmetry. Okay, so an example of a graph with a relation with an x-axis symmetry is those sideways parabolas you looked at in Algebra 2 last year. Whenever you had x equals y squared. When you had that happen, you had these sideways looking parabolas kind of like this right here. And algebraically, if you want to go and test and see if something is or has x-axis symmetry, what you need to do is you need to plug in negative y, and then you need to see if that comes out to the same equation or not. The same equation or relation or whatever you got there. So let's try it out here with this here. So I'm going to plug in negative y. You're going to substitute instead of y, plug in negative y, and then you're going to square that. And since you square that negative, square and negatives make those become positive. And since that comes out to the same exact equation as what we started with, algebraically we just verified that this has x-axis symmetry. Okay, so this next one here, y-axis symmetry, let's do one we've seen a lot since Algebra 1, honestly. You got y equals x squared. That is a parabola. That's one that's kind of going, I guess, opening upward. And algebraically, it's slightly different but similar. You're going to plug in negative x. And then you're going to ask yourself, do you get the same equation again? Okay, so let's try it out. Y equals negative x squared. And that does come out to y equals x squared again. Since that comes out to the same thing, we just verified that y equals x squared does have y-axis symmetry. Okay, now origin. Good example that we saw in Algebra 2 a lot is y equals x cubed. Okay, if you remember back from Algebra 2, you saw this here a little bit. This is the one that kind of curves there, and then it curves back up right there. All right, this has a rotational based symmetry. If you rotate that 180 degrees, it looks like the same graph. Now, as far as algebraically, it's a little bit different. Instead of plugging in just negative x or just negative y, you plug in both. You plug in negative x and negative y, and then you ask yourself, is it the same equation? So let's try it out here. Negative y equals negative x, and then you're going to cube it. Now, since you are cubing a negative number, what's a negative times one more negative? It stays negative. Now, if you're looking at the equation, that's not the same. We can do one more step. We can divide both sides by -1 or multiply by -1, and that would get us y equals x cubed. That does match, so we're good to go right there. X cubed has origin. This type of symmetry. So this next page, we're going to pretty much do the same thing here. The examples get a little bit more interesting here. Some different types of parabolas. Maybe the parabolas are moved, and then we're going to go and verify these algebraically. Okay, so let's try it out here. On example 5, or I guess A right here, we have x squared plus 2. It appears to me like it's symmetric across both sides of your y-axis. So I'm going to say, I'm going to assume that it's y-axis symmetry, and then I'm going to go and test it out algebraically. I need to show. And that one was plug in negative x. If you go back to your notes, sometimes you're going to need to go back to your notes for this one, for this lesson here. Eventually you'll get it to where you memorize. And since that matches right here, that matches this right here, this is truly y-axis symmetry. That's literally all you got to do there. Okay, now B. B is very similar here. Notice the equation's not set equal to y, but that's not really that big of a deal. This one to me appears that if you rotate it, 180 degrees, you should get the same graph here. So I'm going to say that this is one of the rotational ones around the origin. Okay, so you got your x in y equals -6, and for the origin, remember you plug in negative x and negative y, and that comes out negative x times negative y is positive xy, and that does equal -6. That got us back to where we were. Okay, so since that happens, we did confirm that this is has origin type of symmetry. Okay, and then the last one here, you could probably take a guess here. This one's going to be x-axis symmetry. All right, and that's because here's your x-axis right there. There's your axis of symmetry, happens to be the x-axis, so let's verify that one. That one, you plug in negative y, and then equals 1. Visually, it looks like it here. Let's talk about why the algebra works. Sorry about the bell. So here we'll square the negative y right here, and what's weird about this, that becomes positive y squared, but then you got minus. So it does wind up coming back to what we started with right here. So we're good to go here. This is x-axis symmetry. Okay. Now, not all of the types of graphs that we see here, not all the ones that have the different symmetries are true functions. Like example C is not a true function. For the ones that are functions, both of these, we can add a little bit of vocabulary to that. So they also will say y-axis symmetry graphs here, we say that those are even functions. And the ones that have symmetry with respect to the origin, we call these odd functions. And I think that's your new words down here. Graphs of functions can have what types of symmetry? They can have even or odd. Whoops. And remember, even is just with the y-axis, with respect to the y-axis. I would write that down. And then odd is with respect to the origin. Just a little bit of memorization right there. But essentially all this is going to be the same here. Now we're going to go and see, if these are even or odd. Looking at this one here, I had some kids confused here on this one in class. If you go and plot this on your graphing calculator, I believe it moves to the right too, kind of like this. And I had some students say, well, okay, that looks like it's even because it's got y-axis symmetry. It does have a vertical line of symmetry, but it's not the y-axis. It's not the same on both sides of the y-axis. And let me show you why here algebraically and why that works here. So if we wanted to check and see if it's the y-axis symmetry, you're going to plug in negative x. So let's go fx, and then equals negative x. Add negative x in for your x input values right here. Negative x, and then minus 4 times negative x, and then plus 4. And when you simplify that, you get positive x squared, positive 4x, and positive 4. Okay, that does not match right there. So we're going to say that this is neither odd or even as far as the symmetry goes. So that's that there. Let's try another example. This one's not as hard to graph here. So this one here is an x squared graph moved down 4 units. This one actually does appear to have even type of symmetry. Let's go ahead and verify it algebraically. That's plug in negative x again. That's going to be x squared minus 4. So that is the same right there. That matches. So this is truly even. And that's it there on that one. Next one on this one here, this one has the potential to be odd. If you look here at the x cubed, the highest power, this one does have potential to be odd because the highest degree is odd, but it doesn't necessarily mean that it might be symmetric around the origin. We just got to go and test it out. We can look at the graph or we can go and test it out. So we're going to go ahead and try it. Don't know exactly what the graph looks like, maybe something kind of along the lines of that. But for this here to test odd, we need to plug in negative y and negative x. So this one will have a lot of different spots where we're putting our x here. Okay, when you cube a negative, it'll stay negative, so that'll be negative x cubed. We'll have the square right here. We're going to square the negative. That makes it positive, but then you add minus 3, so it's minus 3x squared right there. So it's like the negative 3 made it negative again. Now you got a double negative here, so we can change that to a plus x, and then plus 3. And then just like the previous example, we can divide everything by negative 1. And that basically just changes all your signs around. Okay, so this is your equation here. Now, it's very similar to what you got, but not quite. The negative 3x squared, the negative 3x squared versus 3x squared messed us up, and this negative 3 messed us up. So this one would also be neither. And that's going to be it here for today.